This video is part 1 of the two-part series on Cloudhub 2.0 infrastructure and network. To understand the concepts involved in this video, having a good grasp of basics of networking and the RTF model is a prerequisite. In case if you are unaware of these concepts, please consider watching the previous series on networking and runtime fabric. The topics covered in this video are placed in the timestamp in the description. You can use them to navigate across different sections of this video. So let's get started. Let's understand the architecture of CloudHub 2.0. Now this architecture would remain same for shared and private space. The only difference would be the higher level of control that's possible in the private space. It all starts with an AWS region like US East, US West, APAC, EU, and so on. When it comes to shared space, the clusters are already available in all the regions. But in case of private space, the cluster is provisioned on demand based on the configuration. So whenever you create a private space, Anypoint platform asks you to select the region and enter a CIDR block. This will be used to create an isolated network that is the virtual private cloud. Assume you assigned a CIDR of 10.0.0.0 with a subnet mask of 16. Now behind the scenes, any one platform will reach out to AWS Cloud Formation Stack and provision the required infrastructure. So first it creates a VPC. Now this VPC spans across multiple availability zones. In this case, the region is US East and the availability zones are 1A, 1B, and 1C. The VPC CIDR 10.0.0.0 with subnet mask of 16 that we provided will further be subdivided into 6 subnets. These subnets can be categorized as public and private. So each availability zone will have 2 subnets, one private and one public. Since there are 3 availability zones with 2 subnets each, it makes 6 subnets in total. A private subnet will have 3 components: a control group node, a worker group node, and a network load balancer. The control group and the worker group nodes are created and managed by the EKS formation stack. A control group node is basically an AWS virtual machine that can host control plane components of runtime fabric and Kubernetes. In short, it hosts the pods belonging to the RTF and kube system namespaces. Ingress pod is one such example that belongs to the RTF namespace. Now don't confuse this control plane with the control plane of Anypoint platform. Both are different. To make it clear, currently the diagram that's being discussed is the runtime plane of Anypoint platform, and since this runtime plane is based on RTF model, it relies on Kubernetes. So Kubernetes has its own control plane and runtime plane, which is being represented here as the control group and the worker group nodes respectively. A worker group node can host Mule runtimes where we deploy our Mule applications. Now this controller and worker nodes span across 3 availability zones and are grouped together so that they can scale based on the requirement, and it's done by the auto scaling group. Next is the network load balancer. Now it's a layer 4 load balancer, meaning it can only balance TCP connections and not HTTP connections. The HTTP connections are balanced by the ingress controller that's hosted in the control group nodes. If you use the internal URL, you will be hitting this private network load balancer. Since it is in the private subnet, it can only be accessed from within the VPC, which means that you can access it from the private and the public subnets across 3 availability zones. Access from outside the VPC is not possible as this NLB is only having a private IP assigned to it. But you can access this NLB via a remote office, which should be remote network, which should be connected via a VPN connection. Now let's move our focus to the public subnet. This subnet has two components, a network load balancer and a NAT gateway. NAT gateway is Network Address Translation Gateway. Now the Mule instances hosted in the worker group nodes will need access to the internet. Since the worker nodes reside in the private subnet, they cannot access the internet. In order to allow internet access, a network address translation gateway is provisioned. This network address translation gateway is connected to the internet gateway, and the job of this gateway is to translate the private IP addresses of the worker group nodes to the public IP addresses so that they can access the internet. Since there are three NAT gateway across three availability zones, you can observe that you always get three static public IP addresses whenever you create a public private space, and this would remain as long as the private space is working. Once deleted, this static IPs are lost. The network load balancer here is the same as the network load balancer in the private space, with only exception that it's exposed to the internet via the internet gateway. This facilitates the access to Mule app over the internet. So this is how the Cloudhub 2.0 infrastructure looks at a higher level. All right, now that we have a clear view of the high level architecture, let's understand the traffic flow. This slide shows inbound traffic flow via the public endpoint. In other words, it's incoming traffic from the internet. For sake of simplicity, I have removed the other two availability zones from the diagram. Since the user in this case is trying to access the Mule application over the internet, he will use the public URL. The actors involved in this flow will be the public subnet network load balancer, the controller group node, and the worker group node. Let's understand the IP addresses of these actors. As the traffic has to come via the internet, it will first come to the network load balancer in the public subnet, which means that the network load balancer should have a public IP address. Now, does that mean the network load balancer won't have a private IP address? No, it will have both public and private IP addresses. The public IP address will help the users on the internet to access the network load balancer, and using the private IP address, the network load balancer can access the ingress that sits on the control group node, which is in the private subnet. Next actor in the sequence is the control group node. It will only have a private IP address from the private subnet, private space subnet. That's 10.0.96.0 with a subnet mask of 19. Now, as you know that the controller node hosts the RTF control plane component, and ingress being one such component, it will host an ingress pod, which is MuleSoft's homegrown edge gateway. This pod will have its own IP address from the pod network, and this network usually have IP addresses belonging to the 100 series. In this case, the ingress pod has an IP address of 100.64.186.1. Next actor in the sequence is the worker node. It will only have a private IP address, which is 10.0.96.2 in this case, and it belongs from the private subnet, which is 10.0.96.0 with a mask of 19. This node will host the pods with Mule runtime installed, and the Mule apps are deployed to these pods. So the Mule pod in this case has the pod network IP address of 100.64.87.222. As you observe the pod IP address, it's quite obvious that they belong to a completely different subnet. Basically, they belong to the pod subnet. These pod subnets are interfaced to the node network using the container network interface like Calico. Now that we have a clear view of IP addresses of the participants, let's visualize the whole flow. The client enters the Mule API URL, whose domain would resolve to a public IP address via a public DNS. In this case, the URL got resolved to IP address 54.164.143.130, which is the public IP address of the network load balancer that lies in the public subnet. Observe that the domain got replaced by the IP address. This domain would be retained in the IP packet as host header along with the source and destination IP address. The source IP is the public IP address of the client and destination IP address is the public IP address of the network load balancer. Now the network load balancer will rewrite the IP packet with new set of source and destination IP addresses. In this case, the source will change to the network load balancer's private IP address and the destination will change to the controller node's private IP address. Observe that the NLB is no longer using its public IP address to talk to the controller node that's within the VPC. Along with this, the real IP address, that is the public IP address of the client, is also retained in this IP packet. Once it reaches the controller node, the packet makes its way to the ingress pod that's part of the pod network. So again, the IP packet will be rewritten and the source and destination IP address would change. The ingress node or the edge gateway is a layer 7 load balancer. So it can understand the HTTP request and based on the host header, it will realize which pod to forward the traffic based on the mappings. Since the ingress works at layer 7, it will terminate the TLS session and if the Mule app has its own TLS, then ingress would initiate a new TLS session between itself and the Mule app, which is also known as last mile security. However, let's keep things simple in this case. So the pod IP of the Mule application is resolved by this ingress and the IP packet's source and destination address change again. Now, although the source and destination IP address you see in the IP packet belong to the pod network, this IP packet cannot be directly routed to the Mule application pod. It has to make its way via the controller node, and from the controller node, it has to go to the worker group node. And all of this overhead is being done by the container networking interface. When the request eventually reaches the Mule pod, observe that the host header has changed. Its cluster IP service URL, and this is how pods within the Kubernetes network communicate with each other using the cluster IP service URL. Finally, once the request is processed by the Mule app, the response is sent back to the client. So that's the overall flow of the request. Now it's important that you understand the number of hops that the request is taking within the VPC itself to make its way to the destination. If you compare this with Cloudhub 1.0, well, it's quite complicated now. But again, this is a trade-off that helps in making the system scalable and promotes better utilization of the infrastructure. The inbound traffic flow through the private endpoint. Any Mule app deployed to Cloudhub 2.0 will have two endpoints, public and private. A private endpoint has an internal suffix attached to it and it will always resolve to the private IP address of the network load balancer that is present in the private subnet. This endpoint can be accessed from within the private and public subnets which are part of the parent subnet, that's the private space, also known as VPC. Direct access over the internet is not possible as the private endpoint domain will always resolve to a private IP address. So to enable external access using the private endpoint, the external network should be connected to the private space using a VPN tunnel. Here, the on-premise network is 192.168.0.0 with a subnet mask of 24, which doesn't overlap with the private space network, which is 10.0.0.0 with a mask of 16 bits. Now, the client is in the on-premise network wants to access the Mule application hosted using its private IP address, using its private endpoint. So it will first reach out to the public DNS using the domain name of the app. So this domain name would be private domain name. Observe the internal suffix that's been added. Now this domain will resolve into the private IP address of the network load balancer. Ideally, the domain will resolve into three private IP addresses because there are three availability zones and each has one network load balancer in its private subnet. Now it would be the client's decision to choose one of the IP address. For the sake of simplicity, this diagram only shows one availability zone and the domain name is resolved into only one IP address. But in reality, there will be three and the client would decide which one to choose. A matter of concern here would be that the private IP addresses are published to a DNS server which is public. Now this behavior is same as in Cloudhub 1.0 wherein the Mule worker internal IP addresses were published to the public DNS server. But this won't cause any problem because even if you get hold of the private IP address, you can't do anything unless you are part of the same network. Now, after resolving this IP address, the traffic will make its way to the network load balancer in the private subnet through the VPN gateway. The host header will be of the internal domain. Source address would be the client's private IP address, and the destination would be the private subnet network load balancer's private IP address. The network load balancer will now rewrite the IP packet with the new source and destination address and forward it to the control group node. So this is how the header would look like. Host header remains the same. Source address changes to the IP address of the network load balancer and destination address changes to the IP address of the control group node. The IP address of the client will be retained by the real source address header or maybe the X forwarded for header. The control group node will again rewrite the packet, change the source and destination address to its own IP and the ingress pod IP address respectively and forward the traffic to the ingress pod. The ingress pod being a layer 7 load balancer, it will terminate the TLS session, figure out the correct Mule app based on the domain, rewrite the packet, change the host to the cluster IP service URL, and send the request to the Mule app pod through the worker group node. So eventually, when the request reaches the pod, it will have the following header. Forwarded host will have the original host, that is the domain that the ingress pod was pointing to. Host will have the cluster IP service domain. Real SRC address will have the client's private IP address. SRC address will have the ingress pod IP address and destination address will have the mule pod IP address. So that's how the traffic flows in case of a private endpoint. At a high level, it's quite similar to the public endpoint flow. It's just that we skipped the public network load balancer and used a private network load balancer. And of course, there is a VPN connection involved, which is connected, the external network is connected to the private space using a VPN tunnel. All right, so now let's understand the inbound traffic flow for pod to pod communication. Now, a pod to pod communication can happen in three different ways. A pod can directly use the public endpoint of the Mule application to communicate. It can use the private endpoint to communicate. And thirdly, it can directly use the cluster IP service URL to communicate with the Mule application. So let's take an example. So in this diagram, first of all, I have simplified it a bit. It's slightly different than the previous slide. So now we have the control group node and the worker group node. Worker group node is hosting two different Mule application. One is the first app and the other one is the second app. And the first app wants to communicate with the second app Mule application. All right, and this is how the apps actually look. So this is the pod and this red dotted box represents the whole pod network. So pod network, as you know, belongs to the 100.64.0.0 with subnet mask of 16 subnet. And this is the pod, and inside the pod you have a Docker container. And since this pod is in the control group node and it's an ingress pod, so it has an ingress or Mule edge gateway deployed to Docker. Similarly, the Mule pods have a Docker container and the Docker container has Mule runtime on which the Mule application gets deployed. So now let's take the first case, which is pod to pod communication via the public endpoint. So in this case, let's assume the first app wants to communicate with the second app. So it will use the public endpoint. So this is how the public endpoint looks like. The app name, ignore this. So it has to be the second app. So this is a mistake here. So it should be second app, then a unique string dot unique string dot the zone dot cloudhub dot io. So the first thing first, it has to resolve this domain to an IP address, right? So since this is a public endpoint, the value for the IP address or the A record for this will be there in the public DNS. Now, there's a possibility to have this in the uh, internal DNS as well, but let's assume for this case there is no entry in the internal DNS, rather we'll go to the public DNS. So it has to go to the public DNS. As you know, this pod is hosted in the worker group node, and worker group node has a private IP. So eventually this IP address will be translated to the worker group node's IP address, and this is done by the container networking interface. So since this worker group node only has a private IP address, it cannot reach the DNS server which is on the internet, right? So for that to happen, it needs to get a public IP address. So how does that happen? So it first reaches out to the NAT gateway, which is network address translation gateway. A NAT gateway basically maintains a record. It will map this particular private IP address to its own public IP address. Now, using this public IP address, it can reach to the DNS server. So it basically creates a table, and that table will have the source IP, which who is requesting, and the target IP along with the domain or whatever the query is requested. So this IP gets converted into this public IP address, and finally through the internet gateway, it makes its way to the public DNS server. Public DNS server will basically respond with the public IP address of that particular domain. So in this case, the public IP address is resolved, and it's that of the network load balancer which is present in the public subnet. So again, the flow will be the same. Now using this IP address added with coupled with the host header, the request goes to the NAT gateway since it's a private IP, right? So it goes to the NAT gateway. NAT gateway will send the request to internet gateway, and then it only will realize that this IP address belongs to the network load balancer present in the public subnet. So the request comes back to the network load balancer, which is in the public subnet. Now the network load balancer will send the request to the ingress pod, and we know this, right? This is the same flow that you have seen in the very first slide, which was using the public endpoint, and the flow remains the same. Now it reaches the ingress will finally realize, okay, this is the second app, so it will use the cluster IP service URL, and then it eventually makes its way to the second app. Now, how about the second option, which is to use the private endpoint, right? So in that case, the flow is pretty much the same. Now, if the entry is there in the local DNS, then it's good. If it is not there, then this flow will be the same. So now the domain would have that internal suffix to it, right? And the request will follow the same thing, go to the NAT gateway, internet gateway, and the DNS, get the private IP corresponding to that particular domain. Once it gets the private IP address, this flow will slightly change. Now it won't go to the public subnet anymore. Now, since the network load balancer's private IP address belongs to the same subnet, right? So it will directly reach out to the network load balancer. From the network load balancer, it will reach out to the ingress, and from the ingress, it will reach out to the Mule application pod, right? So this was the second approach. Now the third approach is using the cluster IP service. Now this approach will bypass everything. There's no network load balancer involved, no ingress involved. Directly it calls the application pod because the cluster IP service will directly resolve into the pod IP address. So this is yet another approach. It's quite efficient because you directly call the pod, and the URL format would be the app name dot the environment ID dot svc dot cluster dot local. But it's usually recommended that if you want to communicate from one mule pod to another mule pod and they are part of the same private space, right? So always use the internal endpoint so that it goes via the load balancer and the load gets balanced across the pods. Next up is the outbound traffic flow for pod to internet communication. So I've already covered this. If you see the previous slide, right, wherein we discussed pod to pod communication via the public endpoint. So via the public endpoint is a classic example of pod to internet connection. So what will happen in this case? It's the same as it happens when you use public endpoint for the pod to communicate with another pod. So basically in this case, I have given example.com to be accessed. So first step pod wants to access it. So it basically goes to the DNS, gets the IP address for, I have not shown that DNS step, but you can imagine as seen in the previous slides, right? It will go to the DNS, get the IP address for example.com, use that IP address, then it realizes, okay, it's a public IP, go to the NAT gateway. NAT gateway will change the private IP of this worker group node to the IP address. So 10.0.96.2 will be changed to the public IP address of NAT gateway. NAT gateway, then it goes to internet gateway, and then eventually to the internet. So that's how the outbound traffic flow works for pod to the internet connection. Next up, we have the outbound traffic flow from pod to on-premise device via the VPN. So for example, a Mule application, which is a pod, wants to communicate with the device on the on-premise device. So it has some another application, for example, a database maybe, and it wants to access this. So in that case, it's obvious that it's since it's on-premise to have a secure network, we will establish a VPN, and once we have a VPN, we can directly use the private IP address of that device. So that's how we can talk to other device. So in this case, how would the traffic flow be? So pod IP address source would be 164.87.222. That gets converted into the worker group's IP address. So it becomes 10.0.96.2. Using this IP address, now now it's known that destination is 192 so 68. So the request will be like HTTP 192.168.02. Let's assume there is a REST API hosted by this device. So it will call HTTP 192.168.02 and whatever the endpoint is, and that would be the host, right? So 192.168.02. The destination will be 192.168.0.2 and source would be now 10.0.96. Now it already knows that in the route table of this private space there are entries published from both the parties, right? Due to we had BGP. In case if you have a static table, even in that case there would be an entry. So it will finally figure out, okay, this this IP address 192 has to go through the VPN gateway, so it will directly reach out to the VPN gateway, and from the VPN gateway, it will reach out to the uh, respective device. So now in this case, I have when it reaches this device, right? So the source address would should be 10.0.96.2, which is that of the worker group node. Now this can be different because uh, there is a possibility that this device will not be directly connected to the VPN tunnel. There would be a middle box which could be some sort of gateway or a router device, and that would again override the packet the way this worker group node has done, right, with the pod. So the same thing might happen. So that is why I've written that source address could be 10.0.96.2, or by the time it reaches this device, it would change to the customer VPN gateway IP address. And the destination is obviously, right, it has to reach out to here. So
So that would be the destination, and host would be the same IP address along with the port, because we are directly using the IP address. If we were using the host that gets resolved to the IP address, so that particular host would have been reflected here. So that is how the outbound traffic flows when the request has to go to the on-premise network. It directly goes to the VPN gateway, provided that there is a VPN connection established. So with this, we have pretty much covered all the basics required to understand the Cloudhub 2.0 networking. Now in the next video, I will be taking a deeper dive. We'll be validating all of the things that we have understood in this slide so far. So that would be a hands-on demo. And this was it for this video. I hope you found the content useful. Thanks for watching.